afternoon, and welcome back to CS240. This is Introduction to Computer Systems. And I want to get started off with where we left off. We've got a microservice. We've got a microservice application where we have lots of different services running, and we have different components that are running our service. And you have all the source code for this, and I have instructions that gets you all of these 4 components running. And one of the challenges about microservices is it's tough, because you have 4 different pieces that you have to run simultaneously. And that was one of the disadvantages we talked about microservices. So this disadvantage is that to start the service up, I need to go ahead and I actually have to launch multiple different pieces. So if I take a look at the lecture code for 15, we have a lot of different services. So we have here in the 15, we have a coin flip service. And we talked about this coin flip service quite a bit on Tuesday, where this coin flip service is a really simple service that all it did was flip a coin. So the coin flip service just has flipping a coin. Flip a coin. And then the way this service communicates back to us is it communicates back via a standard interface. We have an interface that basically we get the data. So we actually ask the coin flip service, we want to get the blank, the slash, so get slash, so a blank request. And when we get the request back, we can then talk about how this microservice communicates it back to the game. And we can look at what does this microservice return. Well, when we ask for a get slash, it returns a JSON that says our flip is like heads. So the architecture behind the interaction between the service itself or the game itself and the flip service is that we make a get request to a flip service. The flip service then tells us whether or not we flipped a heads or a tails. And the reason we use a microsystem architecture is now I can give any one of you guys this microservice, the flip service, and if we want to make a way more complicated game, we can make a more complicated game there. So right now it's literally 1 line of code in there, but it could be hundreds of lines of code. It could be thousands of lines of code. We could make a really complicated game that we play. The second service is the Illini coin service. So the Illini coin service now has a few different routes in the source code. So this source code says it's going to take a session ID. And the session ID is a GET request. And we're going to get, a session ID. It's going to return back. It's going to go to the database. It's going to find the user with the session ID. The user doesn't exist. It creates it. And then it sends back the amount and the session ID of the user. So the Illini coin service, when we get from the slash, we know the response is how many coins it has back. So if I do a get slash, I know I can get back the amount of coins that the user has. So like amount is 100. So I get slash, and then I'm going to put an ID. So if I get the ID, then I'm going to return the amount of coins the player has. So I need to have the user's unique ID, and then it will return the number of coins the user gets. And then we can see the other route that we designed in our microservice. If we scroll down here, we have a change, which is a post, so we can change the amount of coins that we have inside of our wallet. And if we change the number of coins in the wallet, it simply updates the amount, updates the database, and sends back the amount. So as I flip a coin, I can also do a post to ID, and I want to change. And then I'm going to have to say inside the change, I need to specify a delta. So delta, I might want to change the coin by -1. So I can either get to the service, and it is going to update the player's count, or it's going to get me the player's amount of currency, or I can post this service, and it's going to change the amount of coins in the player's account. And it's going to give me back at the end, it's going to give me back the amount. So the amount now may be 99 if I change the amount of coins. Yeah? Yeah, you can have the arrows go anywhere you want. Generally, it's best if you can make a tree structure. So you could add, if you added a line where the coin flip communicates with the Illini coin, you could certainly do that. You could add another communication there. The more arrows you make, the more complexity you have. So more interfaces. So generally, a good design principle is you want to minimize the number of interfaces and try and make the structures tree-like as possible. Right, so you see that game basically talks to both coin flip and Illini coin. And if we look at the source code for the game itself, we see that what happens when we play the game. So when we play the game, one thing I didn't do is I didn't verify that we actually have the coins to play the game. So I'm trusting that you have at least a coin in your account. So I'm not doing any error checking here. Then the first thing I'm going to do is I'm going to say, well, if you're going to play the game, I'm going to go to your wallet and subtract an Illini coin. Because remember, the premise of the game is you spend 1 Illini coin, we flip a coin, and if it lands heads, we give you 2 coins. If it lands tails, we keep the coin you gave us. So the first thing I do is I take a coin away from your wallet. Then I actually play the game. So I make a request to the microservice, and I get the coin flip, and then I print out that you flipped a coin, and the result was the coin flip. Then I have the logic itself that says if the coin result was heads, well, I'm going to give you 2 coins. And then I can go ahead and get the information about how many, the player result, I can get how many coins you have left, and I can say you have however many coins remaining after you either got the coins or after you either won or lost. Yeah, that's all on the game. So the game's doing the communication with both the wallet, and with the actual game logic. And you can see that's represented in our architectural diagram, where we have the arrows all spanning from game. So basically, the user interacts with the game. Then the game has a front end itself. The game will display that stuff to the user. And then you're going to, the game logic is going to communicate with the middleware that then eventually communicates with the back end that is the database that stores the amount of coins you own. Yeah, Aaron. Say what? There could be security issues. Absolutely. So right now, we are ignoring security completely. So yeah, you absolutely, so are you thinking security on like users can pretend to be other users, or what aspect of security? Yeah, so there's a lot of security problems that we'd have to address in a real system. That like, one, can you pretend to be another user? Can you mimic someone? Yeah, we just trust the user ID you give us. So you could absolutely mimic someone else. Second security issue, if you're able to access this Illini coin service, you might be able to just send whatever delta information you want. So you can say, hey, I want to give myself 1,000,000 coins. And if I can access that API, I can just give myself 1,000,000 coins. It'd be really easy to say delta is 1,000,000. So yeah, there's a lot of security ideas that you really need to think about. We're going to largely not cover security. So there's courses like 461, I think, is security here. Yeah, 461 is security. It's going to look at many of those attacks. I have a belief that it's really bad to think about security if you haven't done a lot of thinking about security. It's really easy to miss. It's really easy to think you've done security well if you know just a little bit about security and then screw up something that's a really common attack. So you're going to do, like, when you think about security, you're going to want to make sure that no user can access past the front end. You wouldn't want the user to access the middleware directly. You want them to have to go through this box. You would have authentication. You would have all sorts of tokens and passwords and all sorts of other security bits to make sure only the user itself can play the game. And then the other part of security is, do we actually trust the casino? Do we trust that coin flip is actually doing an honest coin flip? Is the game actually rigged? It would be really easy for us to play the game, to play a rigged version of the game. So what we have is so I have sort of two questions about this design. So how is the communication done by the arrows that we've talked about, the game to the two microservices that run the different components of the game? How is that communication done? Yeah, again. Say what? Forks? Ports. Yeah, so it's done via sockets. Specifically, it's not just ports, but what kind of requests? Yeah. API, not just API requests, but yeah, we're making web requests. So the communication is web requests with JSON responses. The exception is then the database is the database communication. So this line right here, this is done with the Mongo API. So we're communicating between the services using web requests. So I make a web request out to the Illini coin service to find out how many coins you have. It's going to give me the response back in a JSON. The database is actually getting communicated by the Mongo API. And the second question is, we've mentioned this a few times, but what kind of service is this? What architecture is this? If we look at these three different services that are all handling in a database, all separate, 4 different services, we would call this a microservice architecture. So this is an example of a microservice architecture. In another world, we could have put all of these in one big application. If we did that, that's a monolithic architecture. If we had things that weren't servers that were running all the time, then we'd have a serverless application. So this particular design, though, I made the choice to make a microservice architecture. And that's what I find most people are using in modern software development, is we see most of the deployment I see is microservice architectures. So one thing that we mentioned quite a bit is when we're building application. Oh yeah, Aaron, go ahead. Will it handle when your amount goes negative? It will just keep counting the numbers negative. So you can go in debt into my casino. Yeah, absolutely. Yeah, you absolutely want to have error conditions in the API. Yeah. Yeah, almost every error. And we'll look at APIs in the last half of this lecture. And yeah, the standard thing is to use the 400 and 500 request codes, or response codes, sorry. 400 and 500 codes to actually indicate errors. Because the 200 code is okay, success. The 400 and 500 are errors. And you usually use those status codes. And you'll also put a message in JSON for the application itself. Yeah, you'll always use, by default, you always just return 200. But if you do get an error, definitely return to 400 or 500. And I think you have to, we have you do that as, like, if you ask for a version that doesn't exist in MP7, I think we have you return an error code in HTTP error code. I think you have to do like 404 or something. So one thing we've been talking about a lot is the different layers. And these are terminologies that you've almost certainly heard before. But every single application we think about as having different layers in the application. And we divide them up into layers because there's usually different technologies that are used for each of the different layers. So for the application layers, we have the first layer is really the front-end layer. So this is the layer that is defined by having, I want to get this exactly right, but that layer is going to be defined by anything whose primary function is the presentation of content to the end user. The primary function is the presentation of content to the end user. So when we think about front-end design, in modern times, we often think of front-end web design, but it doesn't have to be just web design. This could be web. This could be mobile. This could be desktop. This could be any type of different presentation layer. So how do you present the data to the end user? So in our architecture diagram, the game itself is what presents information to the end user. The end user never interacts with anything else except for the game in our microservice architecture. The game communicates with all the other services. The user never interacts with anything except the game itself. The user just plays the game. So whenever you have front-end design, you're going to want to think about what are the challenges or bottlenecks that come with front-end design. So if you are all users of front-end interfaces all the time, every web page you go to is the front end of an application. What are challenges and bottlenecks you've seen in web pages? Yeah. So user friendliness, I would say, is really, so there's definitely UI UX challenges. I would say that is sort of I'm going to call that kind of a non-technical challenge. It's technical on like how you design the UI and UX, but from or non-systems challenge. Let's put it not that way, a non-systems challenge. That UI UX absolutely needs to be done well. You absolutely need designers. A good UI adds a lot of value. But from a systems perspective, you can have, that's not a bottleneck to the system, unless you actually have a really crummy design, I guess. So I do agree that you need good UI UX. You absolutely need that. You need designers. And like the best thing you can do if you're starting up something is make sure something looks really great. Like make great software. Make the software that looks great as well. So yeah, bad design, the UX, the bad user experience is definitely something. What about system unification? Yeah, Matt.
Maybe like making a mobile site versus desktop site.
So mobile, what do you mean by mobile versus desktop? Oh, so making sure it works on all devices. So there's both the display aspect of it, but have you ever gone to a website that just on the phone just loads really, really, really slow? Or you see like a spinning bar for like literally like 10 seconds on the phone while it like loads a graph or something? Have you experienced this? Yes, no, maybe? Yeah. So I think, yeah, one big bottleneck is I'm going to say that this is the client capabilities. So the client capabilities, this might be the compute power. So obviously, if you have a lot of computation that needs to be done, if you're on an older device or a slower device or a low-end cell phone, they may not have very much processing power to compute all the JavaScript that you need to run or something if you're in a web-based application or an Android app. So one thing is compute power. The other thing is this could be network. So obviously, if your user's on like 3G instead of a 4G or Wi-Fi network, they're going to have a lot less throughput as far as network speed goes. So if your application requires megabytes of data before it shows anything, it's going to be a bottleneck. So obviously, you're going to want to build a good UI to compensate for this. If you absolutely have to have a megabyte of data, you're going to want a UI that has some progress bars. Let the user know how fast it's loading. Let the user know how quickly you're going to get there. So yeah, the client capabilities is one thing. Any other things? Yeah.
So you have to design for the user. So like if they're in America, it has to be all in English. If it's in, I don't know, if it's a maybe age group is a consideration, like you have to consider who's going to actually use the front end.
Yeah. Yeah, so there's options on make sure that it's in the right language. It's appropriate to the right age groups. It's accessible to the right crowd. I'd say that's definitely user interface, user experience design. Absolutely need some of that stuff. So at the bottom of any web page, have you seen that you're like waiting for a resource from like doubleclick.com or something? You're waiting for a resource that doesn't even come from the website that you're visiting? Is that something you've ever seen before? So if you look at the very bottom of the page, you sometimes are waiting for like one resource from one server that might be having trouble. So another big front-end problem, another bottleneck to front-end design is going to be slow responses from servers. So even if the client is very, very capable, if the server that you have isn't responding fast enough, that is going to be a bottleneck to your front end. So the front end's not getting the information it needs. So you might have the client having problems, you might have the server having problems. And then, of course, all of this requires good UI design. But I'm going to say that UI design is sort of not part of systems. We don't think of systems as being the UX or the UI experience. That how do we get the data to the presentation layer? And then you can have designers design your Angular or React or Vue Js application. And they can use the data that you're bringing in as the systems programmer. So our job as systems people usually ends once the application has the data. Then the application just has to decide how to present the data. And that's actually the easy part of the work. So if you're a front-end web developer, you often are just saying, I don't care where the data comes from. I don't care how the data gets to me. I just know that this URL is going to give me the data. And once I get the data from that URL, that is going to be how I process. Then I'm going to just process it and display it to the user. So a front-end engineer wants to make this look really, really nice. They don't care about where the data is or how the data comes from. So what technologies are used for front end? If any of you have done front end, what technology have you used to build front end applications? Yeah. React, yes. So React, that is a JavaScript and JSX framework. Front end framework. So React is huge. The queue, for example, is built in React. So when you interact with the queue, that's a React front end. That's how the queue is built. Any other front ends that you've heard about? So Bootstrap is a CSS library. So Bootstrap is really just the presentation. I would say it's like CSS inside of React or inside of any other of these frameworks, you need HTML and CSS. Bootstrap is a CSS library. So inside React, you're often going to use Bootstrap. So now that's like a layer inside of the front end. Does that make sense? So it's part of the front end, but it's not really a main front end framework. Yeah. Yeah, Angular or Vue. So Vue Js is another front end framework. Angular, it used to be Google's JS framework. Google has since canceled Angular. So Angular is no longer a thing being maintained. So if you're writing new code, I hope you don't write in Angular, because it's a project that Google's killed. Vue.js is kind of the alternative to React. It's sort of, it's not, so React is actually made by Facebook. So this is a Facebook product. So React is Facebook. Vue is, at least tries to claim to be indie. I'm actually not. I'm sure there's a corporate sponsor behind it. I don't know the corporate sponsor behind Vue.js, but certainly not one of the big tech players. Any other frameworks you guys have used for front end? Yeah. Yeah, so there's also mobile things. So these are all web. When you're on mobile, there's something called React Native, where you use React's code to actually program for cell phones. If you want to be even more kind of, if you want to use the Google solution, Google has a library called Flutter /Dart. So Flutter Dart is used for front-end programming on mobile devices. So that's Google's approach to front-end on mobile. These things just care about presentation. They're horrible languages to do processing or systems integration. They're great languages for taking in data that's already been cleaned up and presenting it to the user. The front end's purpose is entirely the presentation. And there's a bunch of other frameworks. We hit all the really big ones. These are the ones that probably 90% of you will likely see. There's other smaller front-end frameworks for other purposes. Yeah, Matt. Yeah, so Swift UI in particular so Swift UI is the UI components that are absolutely entirely front-end. Swift allows you to build front ends. Swift, I feel like Swift sort of spans between front end and middleware, because Swift often does all the computation as well. So yeah, Swift definitely is front end. Yeah. Oh yeah, so what makes this great about presentation? Why is this front-end software? And the reason is because they've designed these libraries particularly to have APIs that make it really easy to deal with data and deal with presentation. Why is it? Yeah, why is it bad at computation? So it's bad at computation, for one, it's in a really high-level language, usually with guardrails around it. So you don't have access to all the system resources. Because like React is designed to run inside a containerized environment. So you don't get access to all of the tools that a system on a different language might provide you. So you're not going to have complete access to the system, and you're not going to have a lot of library calls to help you out there. So yes, are they JavaScript code, most of these? Yes, so you can use all the JavaScript libraries. But if you're doing front-end work, you're going to want to use library calls that make things look pretty. That's easy to respond to a user clicking on something. The idea of these libraries, they save you code. Certainly you could write it all from scratch. You could write this in C. There's no reason you couldn't write a user interface in C. But it would be thousands of lines of code. So these frameworks are just frameworks that help you build software faster, easier, and better. Yeah, Aaron. Would Electron be considered a front-end framework? I actually don't know what Electron is.
And it's like, there's actually what Visual Studio Code is.
Oh, so Electron. Okay, so that's the, is that the front end to like the Chromium stuff probably? Yeah, so it sounds like if it's a UI framework, it sounds like that is a front end on a desktop environment. So it sounds like Electron is a front end that's behind web browsers. So that sounds like a front end for desktop. I actually have not done any desktop programming in like forever. So I don't know that space at all. But that does definitely sound like a framework for front end. So the question is there one front end? When we talk about an application, is there always going to just be one front end? No, absolutely not. No. Many applications have many views. So this can be desktop versus mobile sites. So if you think about visiting some website presents you a completely different view of the site, whether or not you're on desktop or mobile. A lot of websites have an app view versus a web view. So you can interact with a lot of services either by going to its website or visiting the app. The app is a front end, the website is a separate front end. They're all going to interact with the same middleware and backend, but you can have multiple front ends that interact with the same components in the middleware and the backend. So systems design is all about how do we separate these components so that we can reuse as much as possible as we're building cloud scale applications. Because if you're building a web app and you want to have a mobile app, you don't want to redo all your databases. You want to access the same database through the same interfaces. So once you get beyond front end, the middleware is the second layer of application development when we're thinking about large-scale applications, and particularly microservices. And the entire purpose of the middleware is an interface to bridge the front end with back-end services. It's often considered the plumbing of the application. So if you think about like a faucet, the faucet is the user interface. You have water that comes out of the faucet, you turn the knob or you lift the knob, the water comes out of that faucet. The water is not generated by the pipe, but you absolutely have to have the pipe to get the water from the water heater or the water tank to the actual faucet. You as a user don't interact with the water tank. You don't interact directly with the water heater. The water heater may be dangerous. It's probably got 200-degree water in it. You wouldn't want direct water from the water heater. You need some plumbing. You need some intermediate steps to both provide safeguards to you, just like a hot water faucet's not going to let you get water that's too hot. Software, middleware, is going to provide that level of service, where we don't want the user to interact with the database directly. That sounds dangerous. We want the user to interact with the database through a middleware piece of software. So we control what calls are made to the database, and then that is mediated by middleware. So in our framework, our two services, the Illini coin and the flip service, those are middleware. So notice that they have lines that come out from the front end. The front end talks these middleware services. And then, for example, the Illini coin, that service actually then talks to a database. So the database is considered backend. So these are the intermediate step between the front end and the backend services. So if we think about building middleware apps, what are things that we have to be concerned about? What are the bottlenecks of middleware? Yeah. Yeah, so one thing is definitely number of requests. how much data is being sent to the middleware. So if a front end is sending lots and lots of requests to the middleware has to handle all of those requests. You might want to mitigate the number of requests the front end sends. Also, how much data is being returned? So if you return a megabyte of data every single time you make a request, that may be way too much data. That may slow down the application. That's a bottleneck. We have to be concerned about, we want to make a minimal number of requests, both from the client to the middleware and the middleware to the backend, and a minimal number of requests, and the request that we want to get back needs to be reasonably sized. Any other middleware problems? What else do we not love about middleware? What else is hard? Yeah.
Maybe depending on how the data is stored in the database, you have to change the middleware. How access it, if it's like distributed or not.
So depending on how you design the backend, you may have to design different middleware. Definitely. So there's definitely a design component. Scanner, were you going to add something?
Yeah, so you have to consider the kind of the structure of the design. So you have a lot of layers, you have a lot of microservices, but there might be like a time delay between each one as opposed to you combine it all into one on a little bit.
Oh, yeah. So I love this. So I'm going to say this is called a dependency delay. So one of the biggest problems with microservices that I've seen in production is the idea that if we have A needs to request something from B, that requests something from C, that requests something from D, that requests something from E, if each of these requests take 100 milliseconds, none of these requests seem slow by themselves, but the sum of all these dependencies is 400 milliseconds. So if you have this number of dependencies you have to make, or if you have to contact 16 different databases to handle the request, how do you either reduce the number of dependencies, or how do you do all of these requests in parallel so that you make all of the requests at the same time and get them all back after 100 milliseconds and then combine them together? So this is something called dependency delay. And this is a big problem with middleware, is how do we mitigate the delay that we have on being dependent on multiple different resources? So that is one of the huge, so basically looking at a number of requests, looking at a number of dependencies are both big microservices problems. What technologies are we using in middleware? In fact, we built some middleware in this class. What are we using in this class for middleware? Yeah. Yeah, we're using, so Python's a great technology. Specifically, what Python library? Yeah, Flask. So Flask is a great middleware technology. It's really designed around a bunch of libraries that allows us to respond to web requests. Because we have these nice libraries, and one function call, we're able to say anything that wants to route to slash, send it to this function. And we have the ability to call out other services very, very easily. So this is something that Flask is awesome about. Any other technologies for microservices? Yeah. So Django? How do you, I don't, so that's another Flask framework. How do you even spell it? Right. A-N-G-O, I think. Django. So that's a more complicated framework. It usually tries to handle both middleware and front end. So it sort of has, you'll see there's an entire application structure. You have a project structure if you've ever written one of these apps. And it has a front end section, it's got a middleware section. So it tries to be a hybrid framework that sort of that does the middleware and the front end for you. So if you're deploying small apps, it's a great environment because then you have two things handled with one application. So we're using Flask in this class instead because Flask really handles really only does middleware well. It doesn't try and be a front end framework. Cool, any other middleware frameworks? Yeah. Golang is a programming language. So Golang's Golang's like Python in the sense that it's a programming language. It's not really a framework itself. You can certainly build middleware in Golang. If you've ever, yeah. Yeah, I mean, ASP.NET, it's still a program. I mean, yeah, so ASP.NET is kind of a blast from, I don't know, 2015 probably. It sort of is a .NET, it's a .NET implementation for active server pages. So it's sort of in this weird nebulous space. It tries to be both front-end and middleware, I think is where its failures is. ASP.NET is pretty old technology. On the JavaScript side of things, you may have heard of Next.js or Express.js. These are both frameworks that go around routing. How do you handle a route, send it to middleware? Yeah. Ruby on Rails, yeah. So if you're in the Ruby world, Ruby on Rails. Ruby on Rails is absolutely a middleware framework. So these are all, the idea of these is these don't handle the presentation of data to the user. These usually respond with JSON requests, respond with formatted data, and it handles the user's requests for data. So they don't handle user interfaces, they just, so anytime you're returning JSONs, you're probably in the middleware. You're probably responding to requests made by the front end to get the front end data to deliver to the application itself. And is there a single middleware? Do we talk about a middleware? No. Aaron, were you going to ask? Does front end always run on the client? I would say almost always. There's going to be exceptions of like, some of you use, what's the Nginx type stuff? Do you use, is it Nginx here that you can like X window into the Linux systems? Or FastX, do you use FastX here? Yeah, so FastX, like you have a small client-side piece, but most of the server rendering of the front is actually done on the server. So there's exceptions, like FastX is actually rendering, it's just rendering the data being returned by the server. But almost all front end runs on the client. There's very few exceptions, and FastX is one of those, where the server is actually doing the front end work, it's just sending the data directly to the client. Yeah?
Preston, is this, you know what Jekyll is?
Yeah.
Like, is that similar to that, where it's all rendered somewhere else, and then CSS?
Yeah, so Jekyll is actually how I do the 240 website, in fact. So Jekyll is a static site generator. What it does is it takes like markdown files. So Jekyll is, I actually know how to spell this one since I use it a ton. So Jekyll takes markdown files and configurations like YAML files, YAML, and it takes these files and generates an HTML file. And this is done entirely offline. So when I build the 240 website, I take markdown and YAML and configuration files, I build it into HTML, and then I deploy the HTML to the web server. Jekyll, because it doesn't handle front-end user requests, it's not a middleware. The output is actually files. I would say Jekyll is probably best described as a back-end technology that generates a front-end for you to deploy statically. Because it doesn't actively interact with the user. It's entirely isolated from the user experience when you're running Jekyll. The interaction is with the HTML pages Jekyll generates. So Jekyll is completely done by the time the user interacts with it. Does that make sense? Because yeah, the user interacts with HTML pages when you're running Jekyll. So Jekyll is really, I'd say, back-end technology to create, or I don't know, it doesn't really interact with anything. It's not even back-end. It's an app that kind of exists to create front-ends. Yeah, great question. And there's not just one front-end, or not just one middleware. Middleware is composed of tons of pieces. In the email I sent you a really famous Netflix talk. And in that YouTube video, if you want to spend the hour looking at it, or half an hour at 2x speed, you can hear about Netflix, an engineer at Netflix talking about there are thousands and thousands of microservices that they run as middleware. So Netflix has thousands of pieces of middleware. How does the middleware interact with the back or the front end? Usually JSON or other structured format. So you're usually interacting, you might, if it's a web-based front end, you're probably going to make a web request and have an interaction with the front end via web request, but the payload data is going to be JSON, so you might have layers of it. But the actual data itself is usually going to be JSON. In older systems, you might see XML, you might see YAML, but it's going to generally be some sort of structured response, some response where you know what to expect. And then just very quickly, backend. So what defines backend? Backend is anything that provides data storage, compute, or other resources to the app, not accessed by the front end. So anything that provides the compute power or the data access or anything that's not directly accessed by the front end is generally considered the back end. If you think back to your MP6, you've done this. In MP6, you had a simple front end that was basically a web page that interacted with the Flask service that you built, that then interacted with your MP2 solution. So the MP2 solution was the compute resource you used. That was backend technology. Your MP2 is backend. It did the computation of saving the GIF that's hidden inside of the PNG image. The front end, or sorry, the Flask, was the mediation between getting the data, the PNG file that the user uploaded. You then saved that PNG file in temporary directory. You ran the backend. The backend did all the hard work, and you just shipped the GIF file back to the user. You've already done full stack development. You did front end, middleware, and backend. You built all of these things up together. The database in the sample application we built here in class, the coin flip application, that is going to be backend. So backend bottlenecks is going to be lots. So there's lots of backend bottlenecks. It's going to be anything that is dependent on, it's going to be software dependent. Usually the backend is the final step. So if your database is not big enough, you need either more memory or more storage for your database. If you're not converting PNGs fast enough, you need more compute power, you need more CPU resources. There's going to be lots of software-dependent bottlenecks in the backend. And the backend usually doesn't have that many interfaces with the rest of the system. Usually the backend is sort of a terminal node, it's a database. The database may be an entire system in itself, but then you really optimize the database. There's not really that many dependencies among backend services. Obviously, if you make too many requests to the backend, that could slow things down. You might be able to optimize the middleware to make the backend more efficient. But generally, a backend is going to be the service that you're going to optimize as a specific software. So you might build a backend service like the GIF conversion. So what technologies are backend technologies? This is going to be any application, so almost any application can be a backend. So this can be C++ or C. This can be Java. This can be Python. This can be Node. But often you see kind of the more performant languages, not the scripting languages. But like databases aren't generally built in Python. They're not generally built in JavaScript. They're built in C, C++, Java. You see, if you're on a Microsoft stack, you see a lot of C# back here. So any application that does work can be a backend service. The backend service is really the thing that actually does all the hard work. Is there a single backend? No. Big thing is nobody, when you talk about the backend, you're talking about a whole suite of services that do the work for the actual product. There's no single front end. People talk about a front end, there's not one front end. You can talk generally about a front end, you can be a front end engineer. You can be a middleware engineer. You can be a back end engineer. You can be a full stack engineer. If you're a full stack engineer, you're generally going to touch the entire cycle, front end, middleware, and back end. Yeah. What is Spring Boot? I'm actually not familiar with that. Yeah, I definitely post on Discord or the Campus Wire, and I'm happy to kind of look at it. Yeah, what you'll find is that you'll learn the technologies you use a lot, and like Spring Boot, never heard of it. I don't think it may be super common in some spaces. I actually haven't programmed in Java in like 10 years. So if it's Java-based, I almost certainly don't know that ecosystem. Any other questions? So how does the backend interact with the front end? It doesn't. So in a good architectural design, you should not have to have the backend worrying about getting input from the user. So the user is going to do evil things. The user is going to potentially be malicious. You don't want to have the thing that's doing the hard work have to worry about whether or not your request is legitimate. You want to make sure, and this is the key idea behind this kind of layered framework, is the backend shouldn't have to care about whether or not the request it's getting is malicious. The backend should just be able to do its job, and there should be middleware and front end that can help it out. So the backend should depend on the middleware to do security, to do access control. The backend itself should really be optimized to do one thing really, really, really well. So I want to kind of talk about, just very briefly, give you kind of a setup for one thing I want to talk about with you guys on Tuesday, which is I think that we're going to be designing a lot of APIs in this class. You've already interacted with a couple APIs we built. On MP7, or MP8, MP Next, MP8, you'll be interacting with APIs that other people built. So MP6 and 7, we define the API. MP8, we're going to find a little bit of the API that you need to implement, but where you're going to be getting the data is going to be APIs that other people wrote. So part of that experience is I want us to start thinking about what makes a good API design. So I have 3 different APIs. So you're already familiar with APIs. So this is like the Java API you're probably all familiar with, or the C API. Web APIs are the functionality of software where you access via a web interface. So web APIs are just like programming language APIs, except for you access them through a web interface. The big idea, there's no standard way to write an API, at least not yet. There's no document you can go to and say, this is how you document an API. This does not exist. There's something called OpenAPI, which is trying to standardize it. It's really verbose, so I don't think it's going to be successful because you just have to include a crap ton of stuff in your API documentation. I think OpenAPIs look absolutely bloated, and they're really hard to use. Not a good user interface. So, and I'm not the only one who feels this way. Like OpenAPI is a great idea. I think it's not actually going to become the de facto standard. But because there's not a standard, lots of people are doing different things with APIs. And I have 3 APIs here, and I'm going to send out a few more to you today. And what I want you to do is I want you to just look at lots of APIs. Just scroll through them, see things that are common with these APIs. So this is how you interact with other people's software. So the Stripe API is one API that I think is really amazing. It does credit card transactions. So if you want to build a website that accepts credit cards, Stripe will actually do all of the work to process somebody's credit card. There's an API that says basically if you have this user, here's the user's credit card information, make this user's transaction happen. That's what Stripe does for you. It has an API that lets you program a credit card transaction. I want you to just look at the API, see how it looks, see what it looks like. So it's a web page, and just kind of scroll through it, look at a few calls, look at how you might use this API. So this is the reference page to actually do a credit card transaction on Square. Another API that's quite well regarded is the GitHub API. It allows you to programmatically interact with GitHub. Third API is what some people say is the best government ran API, which is the Weather Service API. It gets you weather data based on a whole bunch of things. You can get the forecast, you can get the current weather alerts, you can get historical weather. There's a ton of different weather-related data you can get from the National Weather Service API. So these are some of what the internet and what people other than me consider some of the best APIs out there. I'm going to send a few more as well. And I want the goal of what I want to have that I want to start talking about on Tuesday is I want you to pick a list of 3 to 5 things that you think are really, really good about all of these APIs. Like, what do you like about this documentation? What makes these APIs really good? What are common features that you love to see in API? If you had to use an API, what do you want this API to be? What are the best practices in API design? So look at several different APIs and tell me, and we'll come back here on Tuesday and talk about the best practices of API design. What do you see in these? What are common things you want to have in API? What do you like about it? What makes it a good design? What should we do if we're going to provide an API for you? What do you want our APIs to look at? So I'll leave that. I just want to talk about one final thing just to make sure that everything sort of comes together. So one terminology that you're going to hear used a lot is public cloud versus private cloud. So public cloud is going to be any cloud accessible to the internet. So there's what are called the big 3 cloud providers. So the big 3 cloud providers. Well, there's our good friend, AWS. Microsoft has Azure. And Google has Google Cloud. These are called the big 3. They dominate 80 to 90% of the cloud market space, the public cloud market space. If you want something that exists on the internet, it's going to likely be one of these 3 big 3 providers. But the public cloud is just one piece of the internet. There's also a terminology called the private cloud. And private clouds are ecosystems within a private intranet. So private intranets are anything that just exists to a community within the doors, within the walls of an institution. So for example, here at U of I, we have a huge private cloud. If you're not inside of U of I, you can't access linux.ews.illinois.edu. So linux.ews, this is an SSH service that's provided by the University of Illinois, hosted here on our own private software that you can log into. And this is a platform as a service. They're providing an SSH platform for you as a service. You don't have to maintain it. You don't have to do anything about it. You just use your login, and you have a platform as a service. The platform is an SSH and a machine infrastructure. You don't have to worry about installing the right operating system. You don't have to worry about any of the maintenance of it. Someone else maintains it for you. In 240, you have a VM that you're going to have to use in the final project. You can use it right now. It's a machine that's just exclusively accessed only to you. This is infrastructure as a service inside of a private cloud. So here at the U of I, you have the VM. You can maintain the operating system on that. You can patch the operating system. You have root privileges. You can do anything you want. And then here on the private cloud, we also have software that's private cloud. So the queue, for example. So the queue is an example of software as a service. All you bring is the question you have about an MP. And that software just works. This is sort of, the queue is a, so the queue, that actually runs on Illinois servers. It's publicly accessible, like you can access it outside of Illinois. So really the queue is almost a better example of a hybrid cloud, where you take features of both a public cloud and private. So the queue, you can only log into it if you have an Illinois login. The queue, it's running on Illinois resources. It is, but it's internet accessible. So it's not just so, it's taking the private cloud approach to using an infrastructure as a service that's provided by Illinois, but then letting everyone access it. So it's running on the hybrid private cloud, but it's accessible to the public cloud. So we talked about Linux, we talked about your VMware, we talked about the queue. Then you have PrairieLearn. PrairieLearn is a public cloud storage. PrairieLearn itself runs on AWS. If you look at the IP addresses that you get back from PrairieLearn, you can see it's an AWS service. So it's running on the public cloud. So you're accessing all of these different clouds. These terminologies you've heard are all coming together to build an application.